Hello everyone, in this video we'll be picking up where we left off in section 9.6 with the root test. So here's the root test. We say that the series converges absolutely when the limit as n goes to infinity of the nth root of the absolute value of a sub n is less than 1. We say that the series diverges when the limit as n goes to infinity of the nth root of the absolute value of a sub n is greater than 1, or infinity, which is also greater than 1. And we also say that the root test is inconclusive when that limit equals to 1. Right? So this is very similar to the ratio test, except this time instead of looking at the ratio of a sub n plus 1 over a sub n, we look at the nth root of the absolute value of a sub n. So this is especially helpful when we're looking for series that have the nth powers, right? Okay, so let's look at example A here. So in this case, I'm looking at this and I'm saying, hey, I don't really see how this whole a sub n is to the nth power. But I can do some algebra to rewrite this, right? So the first thing I can do is I can say, okay, well, e to the 2n is equal to e squared to the n, right? Why is that? Well, remember, in general, if I take a to the n to the m, then what do? I multiply. Power to a power like this, I multiply them. So this would be a to the m power. So now in this case, since I have 2 and n, I'm actually kind of going backwards for this rule here, right? Now, once again, so I can leave this one here just for reference. And then another property that we're going to use here is if I have a to the n over b to the n, then that's the same as a over b to the n, right? So in this case, I now see that I have the numerator and the denominator to the nth term, to the nth power, so I could rewrite this as e squared over n to the nth power, right? Because both the numerator e squared is taken to the nth power and n to the n is taken to the nth power. So again, the root test works well for series involving nth powers. Here I know that this is my nth power and this is my a sub n. Right? So remember, for the ratio test, for the root test here, we look at the limit as n goes to, limit as n goes to infinity of the nth root of the absolute value of a sub n. So just like in the ratio test, a lot of times that absolute value is redundant, but we do need that there in case we have negative 1 to the n or something like that. So the limit as n goes to infinity of the nth root, that's right, the absolute value of what's our a to the n. We've rewritten it as e squared over n to the nth power. So it looks like this, right? This is my a sub n, right? So the nth root of the absolute value of a sub n. Okay, so first things first, the absolute value is redundant. So the limit as n goes to infinity of e squared over n to the nth power, and we're taking the nth root of that, right? When I take the nth root of the nth power, they cancel out. That's why this is really good for series that involve the nth powers, because I'm always going to have the nth root canceling out with the nth power. So in this case, I get the limit as n goes to infinity of e squared over n, right? So n is going to get really, really big in the denominator, so this limit is going to 0, right, because e squared is a constant. And so 0 is less than 1. So what does that tell us? The root test tells us that it converges, right? So by the root test, this series, e to the 2n divided by n to the n, converges, right? Okay. So one more here. This one's set up pretty perfectly for us to do the root test because I already have everything to the nth power, right? So again, the root test, I look at the limit as n goes to infinity of the nth root of the absolute value of a sub n, So the absolute value of a sub n is absolute value of n plus 1 over 2n plus 1, all to the nth power, all underneath the nth root. The absolute value is redundant, so I'm just going to rewrite this with the absolute value. So I get n plus 1 over 2n plus 1 to the nth power, all underneath the nth root. Nth power, nth root cancel out. That's why this was a good example for to use the root test. So now I get the limit as n goes to infinity of n plus 1 over 2n plus 1. And then in this case, once again, to evaluate this limit, maybe you're starting to see that this limit will end up being, because the coefficient of n here is 1 and the coefficient of n here is 2, you're starting to see that this limit will be 1/2. If you're not starting to see that, then you can still do that trick that we were talking about where we divide by the highest power of n that we see in the numerator and in the denominator. So in that case, it's n. I do the limit as n goes to infinity of n over n plus 1 over n over 2n over n plus 1 over n, which ends up being 1 plus 1 over n, 2 plus 1 over n. Again, when I take the limit, this goes to 0, this goes to 0, so I'm left with 1/2. Right? So if you're starting to be able to make this step here, I'm okay with it, but if not, you can still keep going. And 1/2 is less than 1. So again, what does that mean? By the ratio test, or it's not by the ratio test, by the root test. The series, the original series here, n equals 1 of n plus 1 over 2n plus 1, the nth converges. Okay, so far, well actually at this point we've learned all of our tests to determine whether a given series converges. So let's talk about all of them. This is a nice chart to help us determine whether a series converges. Right, so the first thing we should always do, I've told you this before, but to always make sure to do the divergence test, because we can easily evaluate the limit, and if the limit goes to 0, then we don't have, if the limit the limit as n goes to infinity of a sub n goes to 0, then nothing happens. We got to do more work. But if it doesn't go to 0, then we're done. Right? All of our work is done. We already know it diverges. Right? So that should be the first test we do. If we get the limit equals to 0, we know we've got to do more work, right? Because that's not a condition for convergence. But if it doesn't go to 0, we're already done. So then it just comes a matter of determining if it looks like the form of a geometric series, right? If it looks like the form of a geometric series, then it looks like this, and then we can easily look at the ratio and determine what the sum is, right? Determine if it converges or diverges. If it converges in this case, then we exactly know the sum. Same thing for the telescoping series, right? In the telescoping series, remember it has this very specific form, right? And if it has that very specific form, then we can determine whether it converges by looking at the limit, right? And if the limit does not exist, then we know that it diverges. But in this case, telescoping series actually always converge, right? So I kind of misspoke there. In this case, if it is a telescoping series, by its form, by it having that super special form, we know that in fact it always converges, right? And this is exactly what the sum is. It's always going to be the first term minus the limit of the nth term, right? And we talked about that in the first section. We talked about series. The P-series test, that's section 9.3. I did not make a video for that because it's relatively easy, right? If I have a series that looks like 1 over n to the p, then if that power p that's in the denominator is greater than 1, it converges. If it's between 0 and 1, it diverges, right? It's that easy. The thing about this, though, notice that I don't actually know what it converges to, right? I just know that it does converge if p is greater than 1. And actually that happens with the ratio and root test as well, right? That's what we just went over. These ratio root tests, they will tell you whether it converges or whether it diverges, or unfortunately if it's inconclusive, but it will not tell you what it converges to, right? So I'll highlight that here. If the p-series, the ratio test, or the root test, in these cases, we do not know what the series converges to, right? We only know that it does converge if it satisfies certain conditions, or it diverges if it satisfies certain conditions, but we don't know what it converges to. And the middle two here, we do know exactly that it converges, and we know exactly what it converges to, right? That's what these formulas tell us, right? So that's a nice little overview of series. Thank you.